Tonight, we're going to explore one of the strangest and most universal patterns in existence, something so common that most people never stop to question it, even though once you notice it, it becomes impossible to ignore. Almost everything in the universe spins. The Earth spins beneath your feet. The moon spins while orbiting the Earth. Every planet in the solar system rotates. The sun turns slowly through space. Entire galaxies revolve like gigantic cosmic storms. Even enormous clusters of galaxies containing trillions of stars drift through slow rotational motion across millions of light years. Rotation appears everywhere, at every scale, in every environment, across every era of cosmic history. And the strange thing is that this should not feel normal. If you imagine the universe from scratch, if you imagine matter scattered through empty space with no instructions and no preferred direction, stillness seems like the more natural outcome. You might expect objects to simply drift, to float aimlessly, to collapse inward under gravity and settle into quiet, motionless structures. But that almost never happens. Instead, the universe twists. It swirls. It circles. Matter curves around matter. Clouds collapse into spinning disks. Stars whirl. Black holes rotate so violently that they drag space-time itself around with them. Rotation is not some rare phenomenon appearing occasionally under special circumstances. It is one of the deepest recurring behaviors in nature. The universe refuses to sit still. And tonight, we're going to understand why. Right now, as you're listening to this, you are spinning through space at extraordinary speed. You don't feel it because your senses were not built to detect smooth, constant motion. They detect changes in motion, acceleration, sudden shifts, jerks and impacts. But constant velocity feels like stillness. The Earth beneath you rotates once every 23 hours and 56 minutes. Not exactly 24 hours as most people assume. The difference is small, only about 4 minutes. But astronomers have known about it for centuries because the stars reveal it night after night. The sky shifts slightly each evening because Earth's rotation is measured relative to distant stars, not just the sun. If you're standing near the equator, the surface of Earth is carrying you through space at roughly 1,038 miles per hour, faster than the speed of sound. At the latitude of cities like London or New York, you're still moving hundreds of miles per hour simply because the planet beneath you is turning. And yet your body feels perfectly stationary. There is no rushing wind, no sensation of movement, no awareness that every second of your life has unfolded aboard a rotating sphere flying through space. The only reason you don't notice is because everything around you is moving together. The oceans, the atmosphere, the buildings, the ground, your own body. There is no relative motion between you and your surroundings, so your nervous system interprets the situation as rest. But you are not resting. You are rotating continuously, every moment of your existence. And Earth's spin is only the beginning. The planet also orbits the sun at roughly 67,000 miles per hour. Every year, Earth travels nearly 584 million miles around the sun in a gigantic curved path held together by gravity. You are moving through that orbit right now, while simultaneously rotating with the planet itself. Even that is not the full story. The sun, carrying Earth and every other planet with it, orbits the center of the Milky Way galaxy at about 230 kilometers per second, roughly 500,000 miles per hour. At that speed, it still takes the solar system around 230 million years to complete one full orbit around the galaxy. The last time the sun occupied its current position in the Milky Way, dinosaurs had only recently appeared on Earth. And the Milky Way itself is rotating too. Hundreds of billions of stars orbiting a common galactic center in a gigantic cosmic disk, stretching roughly 100,000 light years across. A structure so enormous that light itself needs 100,000 years to cross it from edge to edge. And still it turns. Then beyond the Milky Way, entire galaxy clusters rotate. Vast collections of galaxies slowly revolving together across millions of light years. And perhaps even larger structures, the immense cosmic filaments connecting galaxy clusters across the observable universe, show signs of rotational motion as well. The deeper astronomers look, the more universal rotation appears to become. And perhaps the strangest part is that this pattern continues downward too, not just upward toward larger scales, but downward into the microscopic world. Electrons possess angular momentum. Quarks possess angular momentum. Fundamental particles carry something physicists call spin, a property so deeply built into nature that matter itself could not exist without it. At the smallest scales of reality, long before planets and stars formed, angular momentum was already present. The universe seems saturated with it, and if you pause long enough to really think about that, it becomes profoundly strange. Why should this happen at all? Why should matter prefer curved motion over straight stillness? Why should collapsing clouds of gas become spinning disks instead of motionless spheres? Why should galaxies rotate rather than simply falling inward? Why should rotation emerge so reliably that astronomers treat it almost as a default expectation of cosmic structure? Because it does not merely happen occasionally. It happens almost everywhere. Every planet rotates. Every star rotates. Every galaxy rotates. Even asteroids tumble through space carrying angular momentum inherited from collisions and ancient formation processes billions of years old. Some spin so rapidly, they exist right at the edge of destruction, held together only barely against centrifugal forces threatening to tear them apart. Neutron stars spin hundreds of times per second. Black holes rotate hard enough to twist space-time itself. Everything turns. Everything circles. Everything carries motion that refuses to disappear. And tonight's story is ultimately about why that motion survives. Because rotation is not just motion. It is conserved motion. That distinction matters enormously. A moving object can stop if friction slows it down. A rolling ball eventually halts because energy transfers into the surface beneath it and into the surrounding air. But rotational motion in the vacuum of space behaves differently. There's almost nothing to remove it, almost nothing to absorb it. Once a cosmic object starts spinning, it tends to keep spinning. For millions of years, billions of years, sometimes longer than stars themselves survive. The Earth has been rotating since its formation more than 4.5 billion years ago. It has slowed slightly because the moon gradually steals tiny amounts of Earth's rotational energy through tidal interactions, but the spin persists. The sun still rotates because the cloud that formed it rotated. The galaxy still rotates because the primordial gas that built it carried angular momentum billions of years ago. Rotation echoes through time. And to understand why, we need to understand one of the deepest laws in all of physics, a principle so fundamental that it shapes structures from the quantum world all the way up to the largest scales in existence. The conservation of angular momentum. This law is the reason spinning ice skaters accelerate when they pull in their arms. It is the reason neutron stars whirl hundreds of times per second after collapsing. It is the reason planets orbit stars instead of falling directly inward. It is the reason galaxies flatten into disks. And astonishingly, it exists because space itself has a symmetry built into it, a profound symmetry, one so basic that most people never consciously notice it. The universe does not care which direction you face. North is not special. South is not special. Left and right are not special. The laws of physics remain the same regardless of orientation. Rotate your laboratory by 90 degrees or 180 degrees and gravity behaves identically. Light behaves identically. Electromagnetism behaves identically. Space has no preferred direction. And from that simple, beautiful fact, an entire spinning universe emerges. Tonight, we're going to follow that chain all the way down, from planets and galaxies, to gravity and collapse, to Emmy-Noether's theorem, to quantum spin, to the deepest symmetries woven into reality itself. Because the universe does not spin by accident. It spins because the laws of nature almost guarantee that it must. The strange thing about motion in the universe is that the most enormous movements are often completely invisible to us. If the Earth suddenly stopped rotating, every person on the planet would know instantly. The atmosphere would continue moving at over 1,000 miles per hour near the equator. Oceans would surge across continents. Winds stronger than any hurricane in recorded history would tear through cities. The surface of the planet itself would become violently unstable. But because Earth's rotation is smooth and constant, your brain interprets it as stillness. Human perception was never designed to detect steady motion. It evolved to detect changes in motion, acceleration, sudden forces, instability. If a train glides smoothly along a perfectly straight track at constant speed, passengers can forget they are moving entirely. Only when the train speeds up, slows down, or turns do your senses react. The universe exploits this limitation constantly. Right now, you are participating in several enormous motions simultaneously, each layered on top of the others so seamlessly that your mind collapses them into the illusion of rest. The Earth rotates beneath you. The Earth orbits the Sun. The Sun orbits the Milky Way. The Milky Way itself moves relative to nearby galaxies, and our entire local group of galaxies drifts through space as part of larger cosmic flows, stretching across hundreds of millions of light years. You are never still, not for a single second of your existence. And yet psychologically, stillness feels natural because everything around you shares nearly the same motion. This idea, relative motion, is one of the deepest conceptual shifts in physics. Motion itself is not absolute. There is no universal stationary platform hidden somewhere in the cosmos against which all movement can be measured. No cosmic floor, no fixed backdrop. Everything moves relative to something else. If you are floating in deep, intergalactic space far from stars and planets with no external reference points, you would have no way to determine whether you were moving at 1,000,000 miles per hour or perfectly motionless. Constant velocity feels identical to rest. This realization disturbed physicists profoundly when it first became fully understood, because it suggests something deeply unintuitive about reality. Motion is not an intrinsic property in the way we instinctively imagine it. It depends on perspective. And rotation is particularly interesting because, unlike straight motion, rotation can sometimes reveal itself internally. A rotating system produces effects that cannot simply be transformed away by changing perspective. You can feel Earth's rotation indirectly through phenomena like the Coriolis effect, the subtle influence responsible for the large-scale rotation of hurricanes and global wind patterns. A swinging pendulum slowly changes direction over the course of a day because the Earth beneath it rotates. Massive weather systems curve Because the planet itself turns underneath moving air. Rotation leaves fingerprints, and those fingerprints appear everywhere in the universe. Consider Jupiter. Jupiter is so enormous that more than 1,300 Earths could fit inside it. It is the largest planet in the solar system, by far, a gigantic sphere of hydrogen and helium, with no true solid surface, only deeper and deeper layers of compressed gas, transitioning gradually into exotic forms of matter. And yet, despite its immense size, Jupiter spins astonishingly fast. One full rotation takes less than 10 hours. That means parts of Jupiter's equator move at roughly 28,000 miles per hour. The spin is so rapid that the planet visibly bulges outward around its middle. Jupiter is not perfectly spherical. The centrifugal effect of its rotation physically reshapes the planet itself, flattening the poles and widening the equator. Saturn behaves similarly. Even the Sun rotates, though more slowly. But the Sun is not solid. It is plasma, a gigantic sphere of ionized gas where different latitudes rotate at different speeds. Near the equator, the Sun completes a rotation in roughly 25 days. Near the poles, it takes closer to 35 days. This differential rotation twists and stretches magnetic field lines deep inside the solar plasma, storing enormous amounts of energy. Eventually, those twisted magnetic fields snap violently. The result is solar flares and coronal mass ejections, eruptions so energetic that a single event can release energy, equivalent to billions of nuclear bombs, all because the Sun rotates. Rotation is not just passive motion sitting quietly in the background of the cosmos. It actively shapes physical systems. It drives weather, magnetic fields, orbital dynamics, accretion disks, jet formation around black holes, even the shape of galaxies themselves. The universe is not merely moving, it is structured by motion. And once you begin seeing this pattern, it becomes difficult to stop. The moon rotates too, although in a very peculiar way. It rotates once every 27.3 days, exactly matching the time it takes to orbit Earth. This phenomenon, called tidal locking, is why the same lunar face always points toward us. Many people mistakenly assume the moon does not rotate because we never see its far side. But if the moon truly did not rotate, we would eventually observe all sides as it orbited Earth. Instead, it rotates perfectly in sync with its orbit. This synchronization is not rare. Many moons throughout the solar system are tidally locked to their planets. Jupiter's major moons, Saturn's large moons. Pluto and Charon are even mutually locked, permanently showing the same faces to each other as they orbit together. Rotation and orbit are deeply connected phenomena. Both are forms of angular momentum. And angular momentum behaves differently from most other quantities people encounter in daily life, because once it exists, nature becomes extraordinarily reluctant to eliminate it. Imagine throwing a ball through space. In an empty vacuum with no forces acting on it, the ball continues moving forever. Now imagine spinning the ball before throwing it. That spin also continues forever. Not metaphorically, literally forever, unless some external interaction changes it. Space contains no air resistance, no friction, no hidden drag slowing everything down in the background. A rotating object drifting through empty space preserves its angular momentum with astonishing persistence. This is why ancient rotational motions can survive for billions of years. The planets still orbit because angular momentum prevents them from simply collapsing into the sun. The galaxies still rotate because nothing erased the momentum they inherited during formation. Even tiny asteroids preserve ancient spins tracing back to collisions that occurred before complex life existed on Earth. Some asteroids rotate so quickly that astronomers suspect they are barely holding together. Loose piles of rubble spinning near their structural limits. If they rotated slightly faster, centrifugal forces would begin overcoming gravity, and the objects would tear themselves apart. Yet even these unstable spins persist because angular momentum is stubborn. It resists disappearance. And nowhere does this become more dramatic than in neutron stars. When a massive star dies, gravity crushes its core inward catastrophically. A stellar core roughly the size of Earth collapses into a sphere only about 12 miles across. Matter becomes so compressed that electrons and protons merge into neutrons, creating one of the densest objects in existence. But the collapsing core retains its angular momentum. And this changes everything, because when the radius shrinks dramatically, the rotation speed must increase, exactly like a figure skater pulling in her arms during a spin. The effect becomes extreme beyond ordinary intuition. Some neutron stars, called pulsars, rotate hundreds of times per second. Hundreds. Imagine compressing more mass than the sun into an object the size of a city and spinning it faster than a kitchen blender. The fastest known pulsars rotate over 700 times every second. Their surfaces move at significant fractions of the speed of light. Their magnetic fields sweep giant beams of radiation across space like cosmic lighthouse beams. Every pulse detected by radio telescopes on Earth is the signature of angular momentum conservation, operating with brutal efficiency. A slow stellar rotation amplified into something extraordinary, simply because gravity forced matter inward, while angular momentum refused to vanish. And this same principle appears again and again throughout the cosmos. Clouds collapse, rotation speeds up, disks form, stars ignite, planets emerge, galaxies flatten into rotating spirals. The universe continuously converts faint, drifting motion into organized cosmic structure, which raises an unavoidable question. If rotation is this universal, if nearly every large structure in existence spins, then where did all that angular momentum come from in the first place? Because something remarkable is hiding beneath all of this. The universe does not need a special mechanism to create rotation. In fact, the deeper truth is almost the opposite. You would need a special mechanism to prevent it. At first glance, stillness feels like the natural state of the universe. If you imagine matter floating through empty space, you might picture it eventually calming down, settling, coming to rest, especially under gravity. You might imagine giant clouds of gas collapsing inward symmetrically until they become quiet, motionless spheres. But the universe almost never behaves that way. Instead, collapsing matter nearly always begins to rotate faster. Not because something external starts spinning it like a toy top, but because perfect stillness is unbelievably difficult to achieve. Far more difficult than most people realize. To understand this, imagine an enormous cloud of gas drifting through interstellar space. A molecular cloud, perhaps dozens of light years across, containing enough material to eventually form stars and planets. At first, the cloud appears calm, diffuse, almost motionless. But appearances are deceptive. Inside the cloud, countless tiny motions already exist. Small flows of gas, turbulence, slight drifts, random currents moving in different directions. One region moves slightly left, another slightly right. Some particles drift inward, while others curve sideways. The cloud is not perfectly balanced because nothing in nature ever truly is. And this matters enormously because all it takes to create angular momentum is even the tiniest imbalance in motion. If slightly more material happens to drift one way than another, the cloud acquires a small net rotation. Not dramatic, maybe so slow that one complete turn would take millions of years. But the important thing is that the angular momentum is not zero. And once angular momentum exists, nature preserves it with extraordinary stubbornness. This is the key idea. Gravity can pull matter inward, but gravity does not erase angular momentum. Instead, collapse amplifies it. The easiest way to visualize this is with a figure skater. When a skater extends her arms outward, her mass is spread far from her rotation axis. She spins relatively slowly, but when she pulls her arms inward, bringing mass closer to her center, something remarkable happens automatically. She speeds up, not because she pushed harder, not because extra energy suddenly appeared, but because angular momentum is conserved. The same total rotational momentum now occupies a smaller radius, so the spin rate increases. The mathematics demands it. And exactly the same thing happens in space. A giant gas cloud might begin with almost imperceptible rotation, spread across enormous distances. But as gravity compresses the cloud inward, the radius shrinks dramatically. The angular momentum cannot disappear, so the rotational speed rises. Slow drifting motion becomes visible spin. This process is unavoidable. You do not need a special force to create the rotation. The rotation was already there in tiny hidden form. Collapse simply reveals and amplifies it. And here is the truly important point. Perfect stillness would require perfect symmetry. Absolutely perfect symmetry. Every particle moving one direction would need another particle balancing it exactly in the opposite direction. Every tiny sideways drift would need precise cancellation. Every gravitational tug would need flawless balance across trillions upon trillions of particles. The odds of this happening naturally are essentially zero. A collapsing cloud does not need large angular momentum to begin spinning visibly. It only needs the slightest asymmetry. A microscopic imbalance distributed across enormous scales becomes significant once gravity compresses the system. This is why rotation appears almost everywhere in the universe. Not because the universe prefers spinning in some mystical sense, but because perfect cancellation is statistically absurd. Imperfection guarantees rotation. And the moment you realize this, something profound becomes clear. The real mystery is not why things spin. The real mystery would be how anything could avoid spinning. Every star-forming region in the galaxy contains turbulent motion. Every proto-galactic cloud in the early universe experienced uneven gravitational pulls from neighboring regions. Every large-scale structure formed from matter distributions containing tiny irregularities. Those irregularities guaranteed angular momentum, and gravity guaranteed amplification. Together, they created a rotating cosmos. You can actually see this process happening in observations of young stars today. Around newly forming stars, astronomers observe gigantic spinning disks of gas and dust called protoplanetary disks. These structures are everywhere, flat rotating systems surrounding infant stars throughout the Milky Way. The famous ALMA telescope images reveal them in extraordinary detail. Bright rings, dark gaps, vast rotating structures where planets are actively forming inside swirling material orbiting a newborn star. These disks exist because collapsing clouds carried angular momentum. Without angular momentum, the gas would simply fall directly inward into the forming star. No disk, no organized orbiting structure, no planets. But the gas cannot fall straight inward because its sideways motion must be conserved. So instead, it curves around the center. Orbit emerges naturally from conservation, and this same principle scales upward astonishingly well. Galaxies form the same way. In the early universe, gigantic clouds of matter collapsed under gravity. Tiny density fluctuations, only about 1 part in 100,000 stronger than surrounding regions, gradually attracted more material. As matter streamed inward from different directions, small asymmetries generated angular momentum. Again, not large amounts, tiny amounts, but tiny amounts are enough. As these proto-galactic clouds collapsed, their spin amplified. The systems flattened into rotating disks. Stars formed within those disks. Spiral arms emerged. The Milky Way itself owes its structure to this process. The beautiful, flat spiral shape of our galaxy is a direct consequence of angular momentum, conservation acting during gravitational collapse billions of years ago. Without rotation, galaxies would not look the way they do, and the same logic extends even further. Matter falling toward black holes forms accretion disks because angular momentum prevents direct infall. Gas spirals inward instead of plunging straight into the event horizon. Neutron stars spin rapidly because collapsing stellar cores preserve angular momentum. Planets orbit stars because the primordial solar nebula rotated. Moons orbit planets because smaller rotating disks formed around giant planets during formation. Everywhere gravity compresses matter, angular momentum reshapes the outcome. The universe is filled with spinning structures because collapse plus conservation almost inevitably produces rotation. And this leads us to one of the deepest realizations in all of physics. Angular momentum is not merely a convenient rule scientists discovered experimentally. It exists because of a fundamental symmetry built into reality itself. A symmetry so deep that it governs the behavior of everything from electrons to galaxies. The universe has no preferred direction. And from that single elegant fact, the persistence of rotation follows automatically. To truly understand why rotation is everywhere, we need to go deeper than planets and galaxies. Much deeper. Because the conservation of angular momentum is not just some isolated rule physicists discovered experimentally. It is connected to one of the most profound ideas ever uncovered about reality itself: symmetry. That word sounds almost decorative in everyday language. We think of symmetry as visual balance, butterfly wings, snowflakes, reflections in mirrors. But in physics, symmetry means something far more powerful. A symmetry exists whenever you can change something about a system, and the underlying laws remain unchanged. And strangely enough, some of the most important conservation laws in the universe emerge directly from symmetries. This connection was discovered by one of the greatest mathematicians who ever lived, Emmy Noether. In 1918, Noether proved something extraordinary. She showed mathematically that every continuous symmetry of nature produces a corresponding conservation law. Not metaphorically, not approximately, exactly. This became known as Noether's theorem, and many physicists consider it one of the most beautiful insights in all of science. The theorem links abstract symmetries directly to physical reality. If the laws of physics remain the same across time, energy is conserved. If the laws remain the same across space, momentum is conserved. And if the laws remain the same under rotation, angular momentum is conserved. That last point is the one that shapes tonight's story. The laws of physics do not depend on which direction you face. Gravity behaves the same whether you point north or south. Light travels the same speed, whether it moves left or right. Electromagnetism does not suddenly change because you rotate your laboratory by 90 degrees. Space has no preferred orientation, no cosmic up, no universal east or west. Every direction is fundamentally equivalent. And because this rotational symmetry exists, angular momentum must be conserved. This is not optional. It is mathematically unavoidable. The conservation of angular momentum is literally built into the structure of space itself. That realization is astonishing when you stop and think about it carefully. The reason galaxies rotate traces all the way back to the fact that the universe does not care which direction you face. A symmetry of empty space determines the behavior of collapsing stars billions of years later. The connection feels almost magical the first time you encounter it, but the mathematics is extremely precise. And once you understand this, the spinning universe stops feeling random. Rotation is not some accidental side effect of cosmic evolution. It is a consequence of the deepest architecture of reality. Think again about the figure skater pulling in her arms. Most people describe the situation casually by saying she spins faster because she gets smaller. But that misses the deeper point entirely. The important thing is not that she becomes smaller. The important thing is that angular momentum cannot disappear. The universe forbids it. When the skater changes her shape, the rotation speed adjusts automatically because conservation must remain true. Nature balances the equation. Exactly the same thing happens in space. A gigantic cloud of gas drifting through the galaxy may rotate so slowly that the motion is almost invisible. But when gravity compresses the cloud inward, the angular momentum survives. It must survive. As the radius decreases, the rotation speeds up automatically. This is why collapsing matter almost always forms spinning disks instead of motionless spheres. Angular momentum resists direct inward collapse. Material can fall inward easily along the rotation axis, but sideways motion remains trapped in orbit around the center. The result is flattening. Disks emerge naturally. You can see this everywhere in astronomy. Saturn's rings form a thin rotating sheet because orbiting particles gradually settle into a common plane. The solar system is roughly flat because all the planets formed from the same rotating disk. Spiral galaxies flatten into enormous stellar disks because angular momentum organizes matter into orbital motion around the galactic center. One principle, one conservation law, operating across incomprehensible scales. And perhaps the strangest part is that none of this requires large initial rotation. The tiniest asymmetry is enough. This is something many people misunderstand instinctively. They imagine that something dramatic must have started the spinning, some giant cosmic push. But no enormous trigger is necessary. Imagine balancing a pencil perfectly upright on its tip. In theory, it could remain standing forever. In practice, microscopic imperfections guarantee that it falls almost immediately. Tiny vibrations, air currents, thermal motion, minute asymmetries, too small to notice, destabilize the system. Perfect balance is extraordinarily fragile. The early universe behaved similarly. Matter was never distributed with flawless precision. Tiny density fluctuations existed everywhere. Slightly more matter here, slightly less there. Small sideways drifts. Uneven gravitational pulls from neighboring regions. Those imperfections generated small angular momenta throughout the cosmos. And once angular momentum exists, gravity amplifies it relentlessly during collapse. This means the universe does not require a mechanism to create widespread rotation. Imperfection alone is enough, and imperfection is unavoidable. This is why nearly every large-scale structure we observe carries angular momentum. Stars rotate because the clouds that form them rotated. Planets orbit because the solar nebula rotated. Galaxies spin because primordial matter distributions contained tiny asymmetries. Black holes inherit angular momentum from collapsing stars and accreting gas. Everything traces backward through conservation, and conservation traces backward to symmetry. This chain of logic is one of the cleanest and most elegant in physics. Symmetry produces conservation. Conservation produces persistence. Gravity produces concentration. Imperfection produces the initial imbalance. And together, these facts generate a spinning universe. There is something deeply satisfying about this explanation because it removes the need for arbitrary causes. The universe does not spin because of some hidden cosmic engine. It spins because mathematically, it almost cannot avoid spinning. The laws themselves push reality toward rotation once matter begins moving imperfectly under gravity. And this idea becomes even more extraordinary when we realize it extends all the way down to the quantum world. Because angular momentum is not only a property of planets and stars, even fundamental particles possess it. Electrons, quarks, photons. Every elementary particle carries something physicists call spin. But quantum spin turns out to be far stranger than ordinary rotation. Because at the smallest scales, angular momentum exists even when nothing is physically turning at all. Up until now, every kind of rotation we've discussed has been something you can picture. Planets turning on their axes, galaxies slowly rotating through space, stars spinning faster as gravity compresses them. Even neutron stars, extreme as they are, still involve physical rotation in the ordinary sense, matter moving around an axis. But when physicists talk about spin, they are not always talking about that kind of motion. At the quantum level, the word spin means something far stranger. Every fundamental particle in the universe carries angular momentum. Electrons have it, quarks have it, photons have it, neutrinos have it. This property is called quantum spin, and despite the name, it is not literal spinning in the everyday sense. This confused physicists badly when the idea first appeared in the 1920s. At first, the explanation seemed obvious. If electrons carry angular momentum, then maybe electrons are tiny spinning balls, tiny charged spheres rotating around internal axes. But there was a problem. The math became impossible almost immediately. Experiments showed that if the electron were physically spinning fast enough to produce its observed angular momentum, parts of its surface would need to move faster than the speed of light. Not slightly faster, hundreds or thousands of times faster, which cannot happen. Nothing in the universe can exceed the speed of light. It is one of the deepest limits built into reality itself. So the classical picture collapsed. The electron was not physically rotating, and yet somehow it still possessed angular momentum. This is one of the strangest discoveries in all of physics. Quantum spin behaves mathematically like angular momentum. It contributes to conservation laws exactly the same way ordinary rotation does. It interacts with magnetic fields. It transfers during collisions. It combines with orbital motion inside atoms. But it is not mechanical spinning. It is intrinsic, built directly into the particle itself. An electron does not spin because something made it spin. An electron simply exists with spin automatically, the same way it exists with electric charge or mass. You cannot stop it. You cannot slow it down. You cannot speed it up. Its spin is permanent. And this strange property turns out to be essential for the existence of matter itself. Electrons possess what physicists call spin 1/2. This tiny quantum detail controls the structure of atoms through a rule known as the Pauli exclusion principle. The principle says that two identical electrons cannot occupy the exact same quantum state simultaneously. At first, that sounds abstract, but the consequences are enormous. Without it, all electrons inside atoms would collapse into the lowest energy state together. Chemistry would disappear. Atoms would lose their structure. Molecules could not form properly. Solid matter would not behave the way it does. The periodic table itself depends on electron spin. Carbon behaves differently from oxygen because quantum spin forces electrons into different arrangements around atomic nuclei. In a very real sense, your body exists because electrons possess intrinsic angular momentum. Every solid object around you depends on it. Every chemical bond, every biological process, every atom. And yet no one truly knows what quantum spin looks like underneath the mathematics. That is important to understand. Physicists can calculate its effects with extraordinary precision. Quantum electrodynamics predicts electron behavior so accurately that experiments confirm the theory to more than 10 decimal places. The equations work beautifully, but intuitive pictures fail. Quantum spin has no real classical analogy. It is angular momentum without ordinary rotation. The discovery happened gradually. In 1922, physicists Otto Stern and Walter Gerlach performed an experiment that changed everything. They sent silver atoms through a magnetic field expecting their angular momentum to orient randomly, producing a smeared continuous pattern. Instead, the beam split cleanly into two distinct parts. Not every possible orientation, only two, up or down. Quantum angular momentum turned out to be quantized, restricted, discrete. Nature at its deepest level was not behaving continuously the way classical physics expected. A few years later, physicists Samuel Goudsmit and George Uhlenbeck proposed that electrons themselves carried intrinsic spin. Then Paul Dirac incorporated spin naturally into relativistic quantum mechanics in 1928. And something astonishing happened. Spin emerged automatically from the equations. Nobody had to insert it artificially. When quantum mechanics and relativity were combined correctly, spin appeared on its own as a necessary feature of reality. This was a huge clue. Spin was not some weird, accidental property discovered experimentally. It was fundamental. The universe required it. And here is where tonight's story loops back beautifully to everything we discussed earlier. Quantum spin and ordinary rotation are different physically, but mathematically they belong to the same family. Both are forms of angular momentum. Both obey the same conservation laws. Both exist because of rotational symmetry in nature. The same deep symmetry of space that keeps galaxies rotating also governs the intrinsic angular momentum of electrons. That connection is extraordinary. From the largest rotating structures in the cosmos all the way down to the smallest particles known to exist, angular momentum appears everywhere. Stars inherit it. Planets preserve it. Galaxies amplify it. Electrons embody it intrinsically. The universe is saturated with rotational behavior because angular momentum is woven directly into the structure of reality itself. And perhaps that is the deepest answer to tonight's question. Why does everything spin? Because the laws of physics almost guarantee that it must. Once you understand angular momentum, the universe starts looking completely different. You stop seeing stars and planets as isolated objects and begin seeing them as the final stage of an enormous process, a process driven by gravity, shaped by conservation, and organized through rotation. Because stars do not simply appear, Planets do not suddenly materialize. Worlds are built gradually out of collapsing clouds of gas and dust, and throughout every stage of that construction process, angular momentum controls the outcome. Right now, scattered across the spiral arms of the Milky Way, gigantic molecular clouds drift through interstellar space. These clouds are unimaginably large, often spanning dozens or even hundreds of light years. Cold hydrogen gas mixed with microscopic grains of dust forged inside ancient stars long ago. Most of the time, these clouds remain relatively stable, but eventually, gravity begins to win. Sometimes a nearby supernova sends a shockwave through the cloud, compressing parts of it. Sometimes collisions between clouds trigger collapse. Sometimes regions simply grow dense enough that their own gravity overwhelms internal pressure. And when collapse begins, rotation becomes unavoidable. Not because the cloud was spinning dramatically beforehand, but because it was never perfectly motionless to begin with. Tiny asymmetries already existed. Small turbulent motions, slight sideways drifts, microscopic imbalances distributed across trillions upon trillions of particles. At first, these motions are almost meaningless. A cloud might take millions of years to complete a single, slow rotation. But as gravity pulls material inward, the radius shrinks, and angular momentum conservation takes over. The spin speeds up automatically. The collapsing cloud begins flattening into a rotating disk. This flattening is incredibly important. Gravity pulls matter inward equally from all directions, but angular momentum resists inward motion perpendicular to the rotation axis. Material falling toward the center cannot simply move straight inward because its sideways motion must be conserved. So instead, the cloud spreads outward into a disk while continuing to collapse vertically, exactly like pizza dough, flattening as it spins. The result is a protostellar disk surrounding a growing young star at the center. Astronomers observe these structures everywhere. Huge, glowing, rotating disks around infant stars, stretching billions of miles across. The ALMA Observatory in Chile has captured extraordinary images of them in recent years. Bright rings of dust, dark gaps carved by forming planets, vast swirling systems where solar systems are actively being assembled. We are literally watching planet formation happen in real time, and every part of it depends on angular momentum. Inside these disks, tiny dust grains begin colliding. At first, they are microscopic, then pebble-sized, then larger rocky bodies called planetesimals. Over millions of years, gravity pulls these objects together into protoplanets. Eventually, entire worlds emerge, and every one of those worlds inherits angular momentum from the original rotating disk. This is why the planets in our solar system orbit the sun in nearly the same plane. It is why almost all of them move in the same direction. They formed from the same spinning structure. The solar system still carries the memory of the ancient cloud that created it 4.6 billion years ago. Even planetary spin itself originates here. As material accumulated into forming planets, collisions transferred angular momentum into the growing worlds. Some impacts accelerated rotation. Others altered tilt angles dramatically. Earth's rotation likely became stabilized after the giant impact that formed the moon. Uranus may have been knocked sideways by a colossal collision early in its history, leaving it tilted almost completely onto its side. But despite these violent events, the underlying pattern remained. Angular momentum survived. It always survives. And the deeper you look into astronomy, the more universal this pattern becomes. The same physics that forms planetary systems also forms galaxies. Early in the universe, Gigantic regions of gas began collapsing under gravity. Matter flowed inward unevenly from the surrounding cosmic web. Neighboring structures exerted asymmetric gravitational pulls called tidal torques. These tiny imbalances generated angular momentum. Again, not huge amounts, just enough. And once collapse began, those tiny rotations amplified. Protogalaxies flattened into enormous rotating disks exactly the same way protostellar systems do, only on scales thousands of times larger. Instead of forming planets around a star, they formed billions of stars orbiting a galactic center. The Milky Way itself is the product of this process, a rotating structure born from gravitational collapse and angular momentum conservation. And this same story repeats almost endlessly across the cosmos. Accretion disks around black holes form because infalling gas carries angular momentum and cannot plunge directly inward. Moons form from rotating disks around giant planets. Stars form from rotating clouds. Galaxies form from rotating protogalactic matter. Rotation is not some secondary feature added afterward. It is built into formation itself. The universe constructs structure through spin. And perhaps the most astonishing part is that this entire cosmic architecture traces backward to something incredibly simple. Matter was never perfectly balanced. That is all it took. Tiny imperfections in the early universe became galaxies. Tiny asymmetries became stars. Tiny sideways motions became planetary systems. Gravity amplified everything. Angular momentum preserved everything. And over billions of years, those ancient motions became the rotating universe we see today. Most spinning objects in the universe rotate slowly enough that the motion feels almost calm. Planets take hours or days to turn once. Stars often rotate over weeks. Galaxies require hundreds of millions of years to complete a single revolution. But there are places in the cosmos where angular momentum becomes so concentrated, so extreme, that rotation pushes physics to its limits. Neutron stars are among those places. They are the remains of dead, massive stars. When a star several times heavier than the Sun exhausts its nuclear fuel, gravity suddenly wins. The outward pressure produced by fusion collapses, and the core implodes catastrophically in seconds. The outer layers explode outward in a supernova, but the core keeps falling inward, and this collapse is almost unimaginable in scale. A stellar core, originally thousands of miles wide, shrinks down to an object only about 12 miles across. Matter becomes compressed so intensely that atoms themselves collapse. Electrons and protons merge into neutrons, creating a sphere denser than anything most people can truly picture. A single teaspoon of neutron star material would weigh billions of tons on Earth. And throughout this collapse, angular momentum remains conserved. This changes everything. Before collapse, the original star may have rotated slowly, perhaps once every few days. But as the radius shrinks dramatically, the rotation speeds up enormously, exactly like a figure skater pulling in her arms. Only now the effect becomes cosmic. The collapsing core spins faster and faster until the resulting neutron star rotates many times every second. Some rotate hundreds of times per second. The fastest known pulsars spin over 700 times every second. Try to picture that. An object containing more mass than the Sun, rotating hundreds of times each second, while compressed into something the size of a city. Its surface moves at enormous fractions of the speed of light. And these stars do something extraordinary. Neutron stars possess incredibly powerful magnetic fields, often trillions of times stronger than Earth's. As the star rotates, beams of radiation sweep outward from its magnetic poles like gigantic lighthouse beams. If one of those beams crosses Earth, astronomers detect a pulse. Pulse, pulse, pulse. Perfectly regular. These objects became known as pulsars. When the first pulsar was discovered in 1967, the signal was so precise that scientists briefly wondered whether it might be artificial. The pulses arrived with astonishing regularity, like a cosmic clock. But the explanation turned out to be even more remarkable. The signal came from a rotating neutron star, a dead stellar core, preserving angular momentum so perfectly that decades later, we can still detect its rotational rhythm from thousands of light years away. And neutron stars are not even the final extreme. Black holes rotate too. When massive stars collapse far enough, gravity overwhelms every known force completely. Matter compresses beyond the point where neutron pressure can resist collapse, forming a black hole. And if the original star carried angular momentum, the black hole inherits it. This produces something deeply strange. A rotating black hole does not merely spin internally like an ordinary object. According to general relativity, its rotation twists space-time itself. The effect is called frame dragging. Space near the black hole gets pulled around by the rotation, almost like water spiraling around a drain. The faster the black hole spins, the stronger the distortion becomes. Some black holes rotate near the theoretical maximum allowed by physics, and surrounding many black holes are accretion disks, gigantic rotating structures of superheated gas spiraling inward. These disks become unbelievably energetic. Friction and magnetic turbulence heat the gas to millions or even billions of degrees. Matter falling toward the black hole releases enormous amounts of energy before crossing the event horizon. In fact, accretion disks around supermassive black holes can outshine entire galaxies. Quasars, some of the brightest objects in the universe, are powered by this process. And again, angular momentum is the reason the disks exist at all. Without angular momentum, matter would simply fall directly inward. But because the gas carries sideways motion, it enters orbit instead, forming a rotating disk. Conservation shapes the entire system. Even the enormous jets launched from some black holes depend on rotation. These jets, beams of high-energy particles, moving near the speed of light, emerge along the black hole's rotational axis and can extend for millions of light years into space. The engines driving them ultimately trace back to angular momentum. And what becomes increasingly clear is that rotation is not just common in the universe. It becomes more dramatic as gravity concentrates matter. The stronger gravity becomes, the more extreme conservation effects become. Clouds collapse into stars. Stars collapse into neutron stars. Matter spirals around black holes. And at every stage, angular momentum transforms gentle drifting motion into extraordinary rotational power. The universe continuously takes tiny ancient asymmetries and amplifies them into some of the most violent phenomena in existence. And yet, despite all this violence, the underlying law remains beautifully simple. Angular momentum survives. Always. That persistence is one of the deepest patterns in nature. A faint rotational drift, present billions of years ago, can still shape the behavior of a galaxy today. The slow spin of an ancient stellar core can become a pulsar rotating hundreds of times per second. The motion changes form. It changes scale. It becomes concentrated, transferred, redistributed. But it does not vanish. Because the universe guards angular momentum with extraordinary loyalty, there is a strange irony hidden at the center of this entire story. The universe spins because it is imperfect. If the cosmos had begun in a state of flawless symmetry, perfectly balanced in every direction, with every motion cancelled exactly by an equal opposite motion, then large-scale rotation might never have emerged at all. Stars might not have formed the same way. Galaxies might not have flattened into spirals. Planetary systems might never have developed organized orbital planes. But perfect symmetry almost certainly never existed. And in many ways, that imperfection is the reason structure exists at all. The early universe, shortly after the Big Bang, was astonishingly smooth. Observations of the cosmic microwave background radiation show that matter was distributed with incredible uniformity. Temperature differences across enormous regions of space differed by only about 1 part in 100,000. That smoothness is almost difficult to comprehend. Imagine an entire ocean where the tallest wave differs from the average water level by less than the thickness of a sheet of paper. That was the early universe, and yet those tiny fluctuations mattered enormously because gravity amplifies imperfections. Regions that were slightly denser than average attracted slightly more matter. As they grew denser, their gravity strengthened further, attracting even more material. Over hundreds of millions of years, tiny irregularities evolved into stars, galaxies, and clusters of galaxies. Everything large in the universe traces backward to those ancient imperfections, and angular momentum emerged from them naturally. Matter did not collapse inward perfectly symmetrically. Gas streamed in from uneven directions. Neighboring regions exerted slightly unbalanced gravitational pulls. Small sideways motions accumulated. Tiny asymmetries became rotation. Then gravity amplified the effect. This idea changes the way you think about the cosmos, because order in the universe often emerges not despite imperfection, but because of it. Galaxies exist because matter was not distributed perfectly, evenly. Stars form because clouds are turbulent rather than perfectly balanced. Planets emerge because rotating disks develop instabilities and clumps. Even life itself depends on asymmetry at fundamental levels. Chemistry relies on uneven electron distributions. Biological systems rely on gradients, imbalances, flows of energy. Perfect equilibrium is strangely lifeless. The universe creates complexity through imbalance, and nowhere is this more visible than in rotation. A tiny asymmetry spread across an enormous cloud becomes a galaxy turning through space billions of years later. A faint, rotational drift inside a collapsing stellar core becomes a pulsar spinning hundreds of times every second. Gravity takes microscopic irregularities and magnifies them into cosmic architecture. And once you recognize this pattern, something profound becomes clear. The universe is not static underneath its surface. It is dynamic all the way down. Motion is fundamental. At every scale, matter flows, curves, rotates, oscillates, vibrates. Electrons occupy probabilistic orbitals around nuclei. Planets sweep around stars. Stars orbit galaxies. Galaxies move within clusters. Clusters drift along cosmic filaments, stretching across the observable universe. Stillness is largely an illusion, created by limited perspective. Even objects that appear stable are full of motion internally. A rock sitting motionless on the ground contains vibrating atoms. Electrons move through quantum states. The Earth carrying the rock rotates through space while orbiting the Sun. Nothing is truly still, and perhaps this is why rotation feels so deeply woven into reality itself. Angular momentum is not just another physical quantity like temperature or pressure. It is tied directly to how motion organizes in a universe without preferred directions. Space does not distinguish left from right. The laws remain unchanged under rotation. And because of that symmetry, angular momentum persists. The universe remembers motion. That memory can survive for billions of years. The Earth still rotates because of ancient motions inherited during formation. The Milky Way still turns because primordial matter clouds carried angular momentum long before the solar system existed. Even black holes preserve the spin of material that fell into them eons ago. Rotation becomes history written into motion. And in some sense, every spinning object around you carries a story stretching backward through cosmic time. The Earth's rotation traces back to the solar nebula. The solar nebula traces back to older stars that enriched interstellar gas. Those stars trace back to earlier generations of cosmic structure formed from primordial matter fluctuations after the Big Bang. Every rotation is connected. Every orbit is part of a chain. The universe we inhabit today is not separate from the early universe. It is the early universe evolved. Ancient asymmetries still echo through present motion, and perhaps that is one of the most beautiful consequences of angular momentum conservation. The cosmos cannot fully forget its past. Motion survives. Patterns persist. Tiny ancient imbalances continue shaping reality billions of years later. A spinning galaxy is not merely rotating through space. It is carrying the memory of the imperfect conditions that created it near the beginning of cosmic history itself. One of the deepest ideas hidden inside angular momentum conservation is that the universe has memory. Not memory in the conscious sense, of course, but physical memory. Motion leaves traces that survive astonishingly long periods of time. Here on Earth, we are used to movement fading away quickly. A spinning top slows down. A swinging pendulum eventually stops. A bicycle wheel loses rotation after a few minutes. Friction erases motion constantly around us. Air resistance steals energy. Surfaces rub against one another. Heat drains organized movement into randomness. Because of this, humans instinctively think of motion as temporary. But space changes everything. In the vacuum of space, there is almost no friction. Nothing rubs against a planet as it rotates. Nothing pushes against a drifting asteroid strongly enough to erase its spin. Nothing acts like air resistance for galaxies. And because of that, motion survives for incomprehensibly long periods of time. The Earth has rotated continuously for over 4.5 billion years. A day was once much shorter in the distant past. Fossil evidence suggests Earth rotated faster hundreds of millions of years ago. Tidal interactions with the Moon have gradually slowed the planet down over immense stretches of time. But the slowing is tiny. The spin persists. The Moon itself preserves ancient orbital motion inherited during formation. The planets continue orbiting the Sun because almost nothing exists to remove their angular momentum. The solar system behaves like a gigantic machine still running on motions established billions of years ago. And galaxies preserve even older memories. The Milky Way's rotation traces back to the collapse of primordial gas in the early universe. Every orbit of every star around the galactic center carries information about ancient gravitational interactions that happened long before Earth existed. In a very real sense, galaxies are fossils of motion. Their structure reflects the angular momentum they inherited during formation. Even collisions preserve memory rather than destroying it. When galaxies merge, their stars are thrown into new orbits through complicated gravitational interactions. Spiral structures may become distorted or destroyed. Ordered motion becomes more chaotic, but the angular momentum itself survives. It gets redistributed, transferred, spread through new orbital patterns. Conservation remains true, always. This persistence gives the universe a strange continuity across time. Ancient motions never fully disappear. They evolve, they transform, but traces remain. And nowhere is this more dramatic than with black holes. A rotating black hole preserves angular momentum from everything that formed it and everything that later falls into it. Gas spiraling inward transfers rotational motion into the black hole itself. Over time, enormous amounts of angular momentum accumulate. The black hole becomes a kind of cosmic archive of past motion. And because spinning black holes twist space-time around them, the memory becomes physically embedded into the geometry of the surrounding universe. Rotation literally reshapes reality nearby. This idea would have sounded absurd before Einstein, but general relativity revealed that space-time is not a passive stage where physics happens. It is dynamic, flexible, responsive to matter and energy, and rotating matter affects it differently from stationary matter. A spinning black hole drags space-time around with it through frame dragging. Nearby orbits become distorted. Matter swirling inward aligns with the rotational geometry of the black hole itself. Even space-time remembers motion. And this strange persistence appears again at the quantum level too. Electrons possess intrinsic, angular momentum permanently. Quantum systems preserve angular momentum through interactions with extraordinary precision. Particle collisions obey strict conservation rules. The universe keeps perfect rotational bookkeeping. Nothing escapes the accounting. This consistency is one reason physicists trust conservation laws so deeply. They have survived every experimental test ever performed. Particle accelerators, atomic spectroscopy, astronomical observations, quantum field theory, general relativity. Everywhere physicists look, angular momentum conservation holds. That reliability is astonishing when you think about the scales involved. The same principle governing a child spinning in a chair also governs neutron stars, black holes, and quantum particles. One symmetry, one conservation law, operating across the entire cosmos. And perhaps this is why rotation feels almost unavoidable once you understand the deeper structure behind it. The universe does not merely allow spinning systems. It preserves them aggressively. Once matter acquires angular momentum, nature becomes extremely reluctant to erase it. Gravity can amplify it. Collisions can redistribute it. Magnetic fields can transfer it. But the total survives. The cosmos remembers. And this realization changes how you look at motion itself. A spinning planet is not just turning randomly through space. It is carrying ancient information forward through time. A rotating galaxy is the visible consequence of tiny asymmetries present billions of years ago. Even your own existence depends on preserved angular momentum inherited through countless layers of cosmic history. The Earth rotates, the Moon orbits, the Sun circles the Milky Way. The Milky Way drifts through the larger universe, and every one of those motions connects backward through an unbroken chain of conservation stretching almost to the beginning of time itself. The universe is not static matter sitting quietly in space. It is history in motion. By this point, the universe no longer looks random. The spinning planets, the rotating stars, the flattened galaxies, the swirling accretion disks around black holes, all of them emerge from the same underlying principles repeating across different scales. Gravity pulls matter inward. Angular momentum resists direct collapse. Rotation amplifies as systems shrink. And because the universe is imperfect, some angular momentum is almost always present. But there is another layer to this story that makes rotation even more important than it first appears. Rotation does not merely accompany structure in the universe. It helps create structure. Without angular momentum, reality itself would look radically different. Consider the solar system again. If the original solar nebula had possessed absolutely zero angular momentum, the collapsing gas would not have flattened into a disk. Material would have fallen directly inward toward the center from all directions symmetrically. The sun might still have formed, but planets likely would not have emerged the same way. Stable orbital systems depend on angular momentum. Orbit itself is essentially preserved sideways motion. The Earth does not fall into the sun because it continuously moves sideways, while gravity curves that motion into a closed path. Without angular momentum, there are no stable long-term orbits. And this principle scales upward too. Galactic disks exist because rotation organizes stars into coherent orbital structures. Spiral arms emerge because stars and gas rotate through density waves inside the galactic disk. Even the visible shape of galaxies depends heavily on angular momentum. Without large-scale rotation, spiral galaxies would not exist as we know them. The night sky itself would look different, and rotation shapes smaller scales too. The Earth's spin affects climate patterns through the Coriolis effect. Global winds curve because the planet rotates beneath the atmosphere. Ocean currents organize partly through rotational dynamics. Hurricanes become rotating systems because Earth spins. Even weather depends on angular momentum. The same is true for stars. The sun's rotation twists magnetic field lines through differential rotation. Plasma near the equator rotates faster than plasma near the poles, stretching magnetic structures until they erupt violently as solar flares and coronal mass ejections. Some of the most energetic events in the solar system are powered indirectly by rotation. And then there are black holes. Without angular momentum, matter falling toward a black hole would disappear almost silently. But because infalling gas carries rotational motion, enormous accretion disks form instead. Those disks heat up to extraordinary temperatures. Magnetic fields intensify. Jets launch across intergalactic distances. Quasars blaze brighter than entire galaxies. Rotation transforms black holes from invisible gravitational traps into some of the most luminous phenomena in existence. Again and again, angular momentum does more than preserve motion. It organizes matter into complexity. This is why the universe feels alive with structure rather than collapsing into simple, featureless arrangements. Rotation creates systems, stable systems, persistent systems, complex systems. And perhaps nowhere is this more philosophically strange than at the quantum level, because quantum spin does not simply influence matter. It determines whether matter can even exist in stable forms. The Pauli exclusion principle, which arises from the spin properties of electrons, prevents atoms from collapsing inward. It forces electrons into layered quantum states around nuclei. Chemistry emerges from those arrangements. Biology emerges from chemistry. Life emerges from biology. In a sense, quantum spin helps create the possibility of complexity itself. Without it, the material universe as we know it disappears. So when we say everything spins, that statement becomes deeper than it first appears. Rotation is not just common. Angular momentum helps shape reality at every level, from electrons to galaxies, from hurricanes to black holes, from planetary orbits to the structure of atoms. The universe builds itself through conserved motion, and perhaps this is why the story feels strangely elegant once all the pieces connect. A symmetry of space creates conservation laws. Conservation laws preserve angular momentum. Gravity amplifies tiny asymmetries. Rotation emerges naturally. Structure forms. Stars ignite. Planets orbit, galaxies turn. Life eventually appears on at least one rotating world, orbiting one rotating star inside one rotating galaxy. All because the laws of physics do not prefer one direction over another. The chain is astonishingly simple, and yet its consequences produced nearly everything familiar in the cosmos. The Earth beneath you rotates because of it. The sun shines inside a rotating galaxy because of it. Even the atoms inside your body exist in stable form because of angular momentum at the quantum scale. Rotation is not some side feature added onto the universe afterward. It is woven into the architecture from the beginning. And the deeper physics goes, the more unavoidable that conclusion becomes. The universe spins because the laws themselves almost demand a spinning universe. Tonight, we followed one of the deepest patterns in the universe, from the largest scales imaginable all the way down to the quantum world. We saw that planets spin, stars spin, galaxies spin, black holes spin. Even the smallest particles in existence carry intrinsic angular momentum woven directly into their identity. And beneath all of it lies a remarkably elegant truth. The universe spins because space itself has no preferred direction. From that symmetry comes the conservation of angular momentum. From conservation comes persistence. From gravity comes amplification. And from tiny imperfections present since the earliest moments of cosmic history comes the rotating universe we see today. Everything turns because the laws of physics almost guarantee that it must. Right now, as you listen to this, you are sitting on a rotating planet, orbiting a rotating star inside a rotating galaxy, drifting through a universe filled with motion at every scale. You may feel perfectly still, but stillness in the cosmos is mostly an illusion of perspective. The universe has been moving since the beginning, and in many ways, it never forgot. If you enjoyed tonight's journey into the physics of rotation, make sure to like the video and subscribe to Science Sleep Theory for more deep explorations into the hidden structure of reality. And as you drift off tonight, remember this: every spinning object you have ever seen, from a child's toy top to a galaxy containing hundreds of billions of stars, exists because the universe itself is built to preserve motion. Good night.